Okay, so to start recorded. Yes. Okay, fine. So I think you can see that white screen. So today actually we will define deformation retraction. So first of all, we define a map called retraction. So what is retraction? So first of all, so let X be a topological space. And say A is a subset of X. You can say the subspace, okay? Subspace of X. Now then a map means here we always say continuous function, okay? We generally do not write continuous. So whenever we say map, that's mean it is assumed that it is a continuous function. Right. Now then a map, oh, say R x to x is called a retraction if R satisfies two following properties. So first of all, R of x, this is totally contained in A. Okay, that's mean that image set is A. That is range is subset of A. Not subset of A, we will actually will be equal to A. Will be equal to A. And the second thing is this is identity whenever you restrict R in A. Okay, so if any continuous function R x to x satisfies these two property, then we will call that map R as a retraction. Okay, now obviously you can see that since the image set is actually A, so therefore you can say, so we can say, or you can consider a retraction as R x to A. Okay, that's mean you can consider R as a map from x to x, or you can consider R as a map from x to A. It is depending on the problems. So if you record R to be x to A, then you can take in that way, or if you need R is a map from x to A, you can take in this way. Okay, so both are fine. So both are fine anyway. If they satisfy these two conditions, then we will say that R is a retraction. Now, can you give me one quick example of retraction? Say my X is say R, or anything. Just give me one retraction.
Constant map.
Sorry?
Constant map.
Right. Now, what you can do, you can take X is any space, right? And you can take your A is a singleton, say X0. Right now, you can take you can define R that X to A by Rx equal to x0 for all x belongs to x. Right, so that's mean you can see that it satisfies the following above two properties. Right, so therefore A is a, that's mean a single point is a retraction of or retract of A. Okay, I should write the another notation. another terminology. So this is called retraction, and in this case we say X retracts to A, or A is a retract of X. Fine. So that's been, and if you take any topological space, it retracts to a singleton set, right? So therefore, actually, this retraction is not very useful in general sense. Okay. Now we have another concept. Yes.
Like, can we say, like, if we have a vector space and we have a projection operator, suppose if we have a vector space which is also a topological space, and we have some subspace and a projector onto that subspace, so will that projector also be a retraction, like onto its range?
Yeah. Right. I think. Yeah. Right. Because if you right, that will be also a retraction. You will have many kinds of map actually retraction. That will also be a retraction if you take the projection map, because if you take that range, then it will be identity, right? And also the image will be only that where it is projecting,
And
right?
like, is this concept of retraction motivated from projector somehow, or like did it develop independently?
Yeah, I think it is independently, because I did not find any relation with this with the projection thing. Anyway, we will see that deformation retraction, then it will be clear. But I do not think it is a generalization of projection. I do not think that. Anyway, we do not know actual what is the actual idea, but my belief is though both are independent.
Actually, for uh, we can say something about orthogonal projections, because in that case, if you are having a vector space, say in an inner product space, and if you are given a closed subspace, then you can write down this space as M, direct sum M par. And in this case, we have a unique representation of every vector. So now, if we define the orthogonal projection operator, in this case, we will have this retraction exactly.
No, no, that is fine. Now he asking that is that retraction, that concept comes from that projection. That is fine. That is, if you have a projection, that will be a retraction in any projection. If you have a vector space, if you can always write it is a sum of direct sum of two vector subspace, and then if you define that projection, then it will be retract. But his question is that is that retraction comes from that projection or not?
Oh, okay. Okay.
Fine. Now we have another concept called deformation retraction. Now this has some geometrical meaning, and this is very important. Okay. So again, so let X be a topological space. Topological space. Then a map. It is called this kind of. So it is not only X cross X comma A. Okay, so I should write first of all. This is a topological space, and A is a subspace of X. Okay. Now then a map we write in this way that x cross I, or we write here 0, 1, 2x is called a deformation retraction if, okay, if it satisfies the following conditions. Now that is very important. Okay. Now first of all, at time 0, the map will be identity. That's mean f of x comma 0, that will be just x for all x belongs to x. Okay. And at t equal to 1, the map will be one retraction. So in other words, we can write that f of x comma 1, okay, it is just belongs to A for all x belongs to A. Right now, since at 1 equal to it is retraction, that's mean we know that f of A comma 1, that is A, right, for all A belongs to A.
Sir,
Yes, and yeah,
fx comma 1 belongs to A for all x belongs to x.
right. Right now, since at 1, at t equal to 1, it will be a retraction. That's when we need this one, right? But it says something stronger than that. That's when it says that not only at 1, in fact, for any time, for any fixed time, it should be identity on A. That is very stronger condition. That's mean if A comma T, that will be A for all A belongs to A. Okay, that's mean at all the time it will be identity on A. Now, if a map F satisfies these three conditions, then we say that F is a deformation retraction. Okay, and here we say X deformation retract to A. Now it is very important in this context, that is the topological algebraic topology. In fact, it is has very geometrical meaning. Okay, for an example, what can you give? Okay, so first of all, if you have a this deformation retraction, now sometimes we say that collection ft that collection is a deformation retraction. Okay, sometimes we say this one as well. This collection is a deformation retraction where that ftx is defined by f of xt. Okay, so when we define say x deformation retracts to A, we can say that via the deformation retraction this capital F, or we can say that via the deformation retraction of this family of, here it will be maps, not paths, right? Okay, now in other words here, now you can see that this one, the definition of retraction, is something similar to the definition of homotopy, right? So only the problem is that here the domain is not I, the domain is X itself, right? So therefore we can think, we will define later, but here also we can say that in this case, so deformation retraction means actually the identity is homotopic to a retraction. And homotopic means in some general sense. Right? It is not our path homotopic. It is something different homotopic. We will define later. This is because we do not need this now. Okay. So now let's see one example. Now say X is my R2 minus 0. 0 means that 0, 0. And say A means the circle, which is that x, y, x square plus y square equal to 1. So this one. Okay. Now, first of all, can you give me one retraction R from x to a?
X by mod x.
Good. Now we can just define x equal to x by norm x. Right? Now, if we define x by norm x, now you can see that that image set is A, that is fine. That property satisfied. Also, if we choose the elements from S1, then that norm will be 1. Right? So therefore, R of A will be A itself because norm of A equal to 1. So we can omit that. Right? So this part is done. Now, so what is actually? So this is my topological space except that 0, and this is my circle. Okay. Now the deformation retraction means so if you choose any points here, that points actually continuously all the points actually continuously coming to this one, and whenever some points here, these points, it moves to this direction continuously. So it move all the points coming to this direction in such a way that it does not, it follows the continuity as well. And similarly, the inside points moves to this way. Again, continuously. That's mean at 0th level, everything will be the identity that whole space X, right? And when time goes, all the points moves towards these directions. And when the time is 1, all the points will be lies only in this green circle. Right? This is the meaning of deformation retraction. And the whole procedure actually is a continuously. That's mean the whole procedure is continuous. So we are not breaking the continuity. Okay. Now, can you define one such deformation retraction f of xt?
We
Yes,
can take linear interpolation. Uh,
right,
Tx plus 1 minus t rx.
right. So we can take 1 minus tx plus t into this. Right? That's mean at the time 0. See, you can put 0. F of x comma 0, that will be, so second part will be 0, so it will be identity. And when x equal to t equal to 1, then it will be only rx, right? And note that for any t, if we choose your a from the set S1, then it will be 1 minus ta plus t again a. So it will be a itself. So therefore it satisfies all the properties of deformation retraction, right? So it is a deformation retraction, and also it is continuous. We have seen that. Since it is in R2, we can check the continuity by the sequence as well. right? Because our topological space is metric space.
Sir, the definition of deformation retraction, do we need f of t in A for all A, or do we need that f of at equals small a for all A?
No, oh, no. Okay, sorry. I should mention that one right here there. So for a fixed t, for any fixed t actually, so f of a comma t equal to a. Did you get this one?
Yes. Yeah.
Right. That's mean whenever at any time, whenever we fix a t, okay. So t can be anything. Then f of xt, f of a t equal to a as well. So in other words, so also that will imply also that if you fixed your a and if it varies your t, then also it will be a as well, right? So it does not matter, I think. Right? Even or I missed your confusion. Is it fine? Or I divert you?
Yes, it's fine. Thank you.
Huh. Okay. Now similarly, you can check that. Now similarly, you can check that if you take Rn minus your this one, okay, that the center, deformation retracts to Sn minus 1. Okay, similarly you can prove this one as well. So fine. Now we will see. So now this is the thing geometrically. Now we will see why this is very useful. Okay, so first of all, we actually prove that if now that is very important theorem. We will prove that that is now our goal to prove that if A is a or you can say that if X deformation retracts to A, okay, then their fundamental groups are same. Then pi 1x is same as pi 1, or better to say that this should be true if both are path connected and say x0 from A, then better to say that in this way. So pi 1 x comma x0 is same as pi 1 A comma x0. Their fundamental groups are same. So that's mean why it is useful. Sometimes it is useful in the sense that suppose you do not know the fundamental group A topological space X, okay, and or it is easy difficult to compute. Then what you can do, you can find a deformation retract of that space, okay, and which is a smaller space, easy to tackle. That's mean easy to find a fundamental group, and then you can say that okay, fundamental group of that X is fundamental group of A. So we are done. For an example, suppose we ask you what is the fundamental group of R2 minus 0, 0. Right, now this space we do not know anything about that, right? So because if you take in this way where this center is removed, right? If you take a loop can be anything, right? It can travel anywhere like this way and again move this way. So geometrically it can be anything, right? It almost can be one two kind of thing as well, right? Because we know that space filling curve. So it can be any complicated one. So what will be the fundamental group of this? Now, for this kind of topological space, we need the deformation retraction. For an example, here, what is the deformation retraction of R2? So here we know that this space deformation retract to S1, right? And we know that fundamental group of S1, that is Z. So therefore, fundamental group of R2 minus 0, 0 is also Z. Okay, is that fine? Is that fine?
Yes, sir.
Okay, so that's mean what we need to prove. We need to prove only this one. So that is very important here. Okay, and you have quiz on Sunday. So we will give one applications of this one as well. So where you have to find that deformation retract and you have to calculate that fundamental group. Okay, so you will have a application of this. Okay. So for this, first of all, we need that induced homomorphism. So we just quickly define that induced homomorphism. That is very simple. What is induced homomorphism? Now suppose you have a topological space, say x comma x0, say y comma y0, z comma z0. Why I am writing this? That's mean here it just means that x0 belongs to x. That's all. Y0 belongs to y. Okay. Now suppose this is my map. Say this is my f, or say this is my say phi, and say this is my psi. Okay. Now why I am writing the order pair? So it just means that phi of x0 equal to y0 and psi of y0 equal to z0. So this is the meaning of this writing. Okay. Now we have this map. Now what if? Now if you have say f belongs to pi1, say x comma x0. Okay. So that's mean f is a loop with base point. F is a loop with base point x0, right? Now that will imply, now if you apply your phi, now this is your loop, now phi composition f. Now what will be that phi composition f? Now f is a loop with base point x0. Now that will imply phi composition f is a loop with base point y0. Is that clear? That is simple, right? And similarly, you can write that psi compose phi compose is a loop with base point z0. Is there any problem, or it is clear? Yes.
Yes, sir. It's clear.
Yeah, because that is simple. Just ask me if you have any doubt. Just ask. Okay. Now that imply if that this belongs to pi1 of x comma x0, that's mean that collection, that class of loops belongs to pi1 y comma y0. Okay. And similarly, psi compose phi compose f, that is belongs to pi1 of z comma the z0. Okay. So therefore we can define. So therefore if we have a map So therefore, if we have a map, say phi, say x0 to y y0, then we can define phi star pi1 y comma y0 defined by pi star f equal to phi composite. We can define in this way. Now, obviously, the first question is why this is well defined. Now, that is also simple. Why this is well defined? Now, we know that if f0 homotopic to f1 by homotopy, say ft, now that imply phi compose f0 homotopic to phi compose f1 by homotopy. Which homotopy? Can you tell me the homotopy?
Phi OFT.
Phi f.
Right. Now phi compose this one only. Right. So therefore, if that if this class, now that imply phi star f0 equal to phi star f1. So that's when the map is well defined. Okay. Now also it is an homomorphism. Why? Now this is again simple. Now tell me what is my phi star fg. So that is phi star f dot g. Now can you tell me? Okay. So first of all, this is by definition phi compose f dot g. Right. Now can you tell me what is this one? What can we write this? Now this can we write?
Phi compose F dot phi compose G.
Right. Now is it clear all of you? Or do you want me to show this? Fine, or shall I show?
So please
Yeah,
show.
it's fine.
Right. Now just that definition of this. So this is my f of 2s, g of 2s minus 1, 0 less than equal to s less than equal to half, half less than equal to s less than equal to 1. So this is s. Now just compose phi, then you will get this. Right? That is simple. Now that is actually then phi compose f, phi compose g, and that will be phi star f, phi star g. So therefore, this is a homomorphism as well. So therefore, phi star is a homomorphism. Okay. Now tell me if phi star is identity. Sorry, if phi is identity. Now if phi is identity. Now what will be phi star? Can you say that it is also identity?
Identity is, yeah.
It is also identity, right? By the construction. Because you can see that here, if this is, if phi is identity, then phi not f will be again f, right? So it is identity. This is identity. Okay. Now that imply also, so now if phi is identity, then phi star is identity. Now this is done. This is simple. And another observation is if you take phi compose psi and star, now you can say that this is phi star compose psi star. That's mean this. So if you have Oh, okay. So here pi1 x, x, x0, y, y0, z, z0. Now we have defined that is psi, that is phi. Now then pi1 x, x0, pi1 y, y0, pi1 z, z0. Right, now this equal to this. Now also you can just use the definition. Then you will get this one as well. Now both these two are fine. Okay, now we will combine these two and we prove that, say, one theorem. So let x and y be path connected topological space. Topological space. Now if x and y are homeomorphic, then pi1 x and pi1 y are isomorphic. Okay, so that's mean if x and y, two topological space, both are homeomorphic, then their fundamental groups are isomorphic. That's mean they have the same fundamental groups. So therefore you can say that that fundamental group is topological invariant. Okay, now actually we have used this one in somewhere, I think, but here is the proof. Now how to prove this one? Now the proof is also simple. Now first of all, now let say phi from x to y be a homeomorphism.
Sir,
Hmm.
so you say fundamental groups are topologically invariant. Instead, we should say algebraically invariant. And we say like this because isomorphism is property of algebra.
Topological invariant means I said that if you have two
So
topological space,
x and y are like topologically same, but pi one x and pi one y are algebraically same.
aha, right. Actually, we assume that pi1 x when they are isomorphic, that's when they are same. We assuming that we are saying that this is topological invariant. Of course, it depends on algebra as well.
Okay.
Okay, so that's when whenever two groups are isomorphic, we assume that they are same. That is the first assumption, and then we are saying that it is topological invariant. So that's when if we have two topological space which are homeomorphic, they have same fundamental group. You can say that. Okay, because when we define that fundamental group, we can define in such a way that we will get that that group. Because we do not need actually that isomorphism. For an example, whenever we are computing that pi1 s1 z, then we define in such a way we get z actually, right? Because that isomorphism, it comes from that constructions only, that construction of fundamental group. Okay. So we assume that phi is a homeomorphism and let psi equal to its phi inverse. Okay. Then what is my psi compass phi? Now that is identity on x. And what is my phi compass psi? That is identity on y. Right? And then psi star compass phi star, that is this star, and phi star compass psi star equal to identity y, that is star. Now that imply, now since both are identity, so therefore phi star is isomorphic, or you can say bijective here, right? Because this is identity. Now, since phi star is bijective and we know it is already a homomorphism, so that implies phi star is isomorphism. Okay. So this is done. Now we actually prove the important one thing. Okay, is this part clear? Any doubt? That was simple. Any problem? Yes.
No, sir. No, sir.
Okay, good. Now here is the statement. We can write it as a lemma. So let X be a topological space and A is a subspace of X. Whenever we are writing in this way, that's when you assume that A has a subspace topology. Okay. And let X0 from A. Okay. And let I A to X be an, or not be an, be the inclusion map. Right? You know the definition of inclusion map, right? That's when IA is just A. It is just a identity map actually, but since the range is codomain is different, so therefore we call it is an inclusion map, right? It is actually identity. If you restrict the codomain into its range. Okay. Now, if X retracts to A, then I star is injective, or we can write where it is I star. Now I star is from pi1 A comma x0 to pi1 x comma x0 is injective. Okay, and if X deformation retract to A, then I star, the same map, is bijective. Or you, another way you can say that phi star is an isomorphism. Okay. Now from this result you can say that if X deformation retracts to A, then both have, that is A and X both have same fundamental group. That's when isomorphic fundamental group. Okay. So here is the proof. Now proof is simple actually. So first part is very simple. Now let R X to, now see here that is important. So that, see, whenever we are taking retraction, the domain, codomain, we can take A or X, both, right? But here that A is useful. So therefore we are taking A, be a retraction. Okay. Now since R is a retraction, that imply R compass I. Okay. Now this from A to A is identity. Is that clear? This is identity. It is just the definition of the inclusion map and the definition of retraction. Okay. Now, since this is identity, so therefore R star compose I star from pi 1 a comma x0 to pi 1 a comma x0. This is also identity. We have seen that, right? Now we need to show that I star is injective. Now what is I star actually? Now I star is a map from pi 1 a comma x0 to pi 1 x comma x0. Okay, now we need to show that both are injective. Now let I star f equal to I star g for some fg in pi 1 a. Now since both are equal, we can apply here R also. Right, now that implies, now since this is identity, so therefore this. So that imply I star is injective. So we are done. Now any problem on this, or is it clear? Yes.
Sir, shouldn't the homomorphism induced by inclusion map always be injective? Like inclusion map by itself is always injective.
That is a good question. Now here we prove that if R is a retraction, R is a retraction, or if A is retract to this one, then it is injective. Now you tell me. Now you give me the answer. If you have inclusion map, then I star is always injective. You give me the answer. What do you feel?
Yeah, I think that
You
if you
think?
have two paths which are homotopic, which are distinct in A,
No,
they are
no.
not
First
homotopic
of
in
all,
A,
first of
but they
all,
become.
see. First of all, tell me what do you feel? Yes or no?
Intuitively, it appears that
True.
it should be.
No, it is not true. Can you give me one example? Quick example. This is not true. Just take x equal to R2 and A equal to S1.
Yes. Yeah, because now, like in R2, any two paths are homotopic.
So its fundamental
Whereas,
group is 0.
hmm,
But if you take
whereas
S1, its fundamental group is Z. So
Z.
that is not true in general. And also from this, you also can now prove that is this is a proof also. So there is no retraction from R2 to S1. Now you actually proved that. Now from this you prove that there is no retraction from R2 to S1. Right? Because if there is a retraction from R2 to S1, then that inclusion verb should be injective. But that is not true. So that's mean there is no retraction from R2 to S1. Clear?
Yes, yeah.
Good. Now this type of questions you should practice. That's mean whenever you read this one, since this is an advanced topic, so we do not have any tutorial kind of thing, right? Now this kind of concept will be coming in the during the exam. The similar concept. Now the question you asked and the question now I told you that there is no retraction from R2 to S1. Now that was a proof of this. So now this type of problems will come during exam. Now, whenever you read, just read carefully. Since I gave you lecture notes as well, go through the lecture notes very carefully and try to think in the reverse way. Now, this is true for this. Then, if you change this one, then will be in this that will be true or not. So, just think in that way. Okay, this is very good question actually. So, this is a very good question to ask. Good. Now we will solve the part 2. So that's mean there is a deformation retraction from X to A. Now let F X cross zero 1 to X be the retraction of X on A. Okay. And let R be the, oh, this is a retraction. Now that will be a deformation retraction.
Range of f will be a, right? Like f will map x cross. Oh, no. Yeah, sorry, it's fine.
That is fine. Okay, and we know that at the point t equal to 1 we have a retraction, right? We let R be the retraction. Okay, we just name it is by R. Now then, so that's what does it mean? So I just use the definition. So f of x comma 0, that was my x for all x. F of x comma 1, that is Rx, again for all x comma x, right? And retraction means I know that again R of x belongs to A and R of A equal to A for all A belongs to A, for all x belongs to x. So this is, we know the property of R. And third number is f of A comma t, that is also A for all x belongs to x. Now we have these three. Okay. Now now what is actually, now what you need to prove? Okay. So we have I star phi 1 A comma x0 to phi 1 x comma x0. So we have this map, right? And we need to prove that I star is, it is, we know that it is injective, right? Now we prove that this is surjective. So that's mean we choose a map, a path from this side, and we will get a pre-inverse. That is the meaning of surjective, right? Now let belongs to phi 1 x comma x0. Okay. So that's mean f is a loop with base point x0. Okay. Now since this, therefore R star f, which is just R compose f, now that is belongs to phi 1 a comma x0. Okay. Now, do you have any ideas of what I am going to prove actually? Any idea? So what we need to find? We have f here and we need to find one pre-inverse this. Okay, that's mean we need to find some element here. Now if we have f, then again we have r star f will be in this. Now actually we'll prove that that is a pre-inverse of this. We will prove this. Okay. Now tell me if we are able to prove that say R compose F is homotopic to F, then are we done? So that is means if this is true, now that imply R not F is same as F. This one, right? Now what will be my I star F? Now I star F will be F itself, right? By the definition, and that is, oh sorry, not, we should not write I star F. Now what is I star R composite? Now since it is in A, so therefore it is R composite F as well, and this is equal to F. So therefore we are done. So if we prove this, then we are done. Is it clear?
Yes.
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 Okay. Now just this is the simple idea. Now what is, we will use this map. We will use this map F. Okay. So first of all, see what is this F? Actually, this map already defined this. So this map is already almost defined this. That's only one problem is that the domain is X, but we need a domain is 0, 1, right? So we need the domain is 0, 1, but it is here domain is X. So we need to just tackle the domain. Otherwise, everything is same. So everything is saying that almost this is homotopic to this by the construction of this. So we need to change the domain. So how to change the domain? We can compose a new map. So now let G 0, 1 cross 0, 1 to X cross 0, 1 defined by G of X comma T equal to Fx comma T. Okay, so this is a map. So we have this situation 0, 1 cross 0, 1 to X cross 0, 1 to X. Now this is my F, this is my G, and we need this to this. So that will be my H. Now define H 0, 1 cross 0, 1 to X by H of X comma T equal to, or we can just write H equal to F composite G. This. Now see, now we are done. Now what is H X comma 0? That's mean F of G X comma 0. Now see the map. So that's mean F of Fx comma 0. Now what is F of Fx comma 0? See the map. It is just X. X comma 0 is X, right? So therefore F of Fx comma 0 is Fx. So that is Fx. Now what will be h of x comma 1. Now that will be f of g of x comma 1. Now that is simple, f of fx comma 1. Now what is f of fx comma 1? Now see the map. See, f x comma 1 is rx. So therefore f of fx comma 1 is r of fx. R compose fx. Right. Now the only thing is need to show that now the first point and the second point. Now what is x of say 0 comma t? Now again this is f of g of 0 comma t. Now that is f of f0 comma t. Now what is f0? Now f0 is x0, x0 comma t. Now that is x0 since x0 in a, and similarly this x0 comma t equal to x0. So we are done. So therefore, so thus f is homotopic to R compose f. So that implies I star is surjective, and since it is bijective, so therefore I star is isomorphism. So we are done. That is a simple one, just a construction. Now tell me if you have any doubt. Yes. So actually retraction map, which we have the deformation retraction, that is actual, that was the actual map that satisfies all the properties of that homotopy. But the only problem was the range domain, because for that path homotopy we needed the domain is 0 1 cross 0 1, because we have paths, right? Paths from 0 1 to x. So therefore we just have a trick. We just define a map in that way, 0 1 cross 0 1 to x cross 0 1, and we define in such a way that xt g of xt equal to fx comma t. That's all. And then we compose the parts and we do everything. Now everything comes automatically actually. So we have not done anything. We just go through the path, right? Go to the direction where it has. Now is that clear?
Hello.
Yes.
So in the first part, we calculated when we write I star f, why can't we write directly I star f is f? Like I star f is defined as I composed with f, then it should be f.
Where?
So in the first part, I like here when we write let I star f is equal to I star g, and by definition of I star f, it is nothing but I composed with f. So like why are we using R star?
But I think they can go into the same homotopy class when you map them to X. So like they might be in different homotopy classes in A. So they'll be distinct paths, but when you map them to X, like if you consider them as paths in X, then they'll be homotopic. So so when we are proving that it is an injective map, we'll have to look at the homotopy classes, that if they are mapped to same homotopy class, then they come from the same homotopy class.
Okay, just a minute. I think I missed something here.
Like in second part we used I star of R composed F is R composed F. That's why can't we use same thing in the first part?
Right, right, right. Just a minute. We cannot write actually. There is some reason, but here I missed something. We cannot write that. So how to write it is injective till or
So, because it was in homotopy class in A, and that we have defined was homotopy class in X. Sorry, loops in X, and here we are dealing with loops in A.
no, but yeah, that is correct. But I think I should mention something, but I'm missing somewhere. Because see, first of all, why we cannot write this directly I star F? Because
So,
look at here. So whenever we have this F, say F is a loop in pi 1a. Okay. And whenever we have that loop in this one, in that pi 1 x comma x0, so I star this one, that if that is fine, if we take only that if where we have taken that if. So homotopy class.
Actually, like when we say that like I star square brackets f equals I star square brackets j. So here in the input, like the homotopy class represented by a square bracket f is a homotopy class in in A, and then the range is a homotopy class in X. So basically, the homotopy
Right.
classes have different meanings in X and A. So in the notation, maybe we can add some subscript X or subscript A
No,
with the
no,
square
that is
brackets.
no, no, that is fine. That is fine here because of their different homotopy classes. We cannot write, but here I have written right. So that is a mistake. That I should not write this one.
Okay.
I
If
should not write this one. So I have to write something else. Uh,
yeah, maybe you can distinguish by using a subscript A or subscript X for the homotopy.
this one should not write this one. Now how to write this then? Okay. Now we get this one. So therefore we get what was
Maybe like for the second part, you can use the result proven in the first part. That like since we have proven that I star is injective, uh,
no,
and
but
now in the second part we are given a deformation retraction, so it is also a retraction.
no, that is the same as R composite. Okay. So what we get? So we get uh, So whenever we have any path in, any loop, f is a loop in pi1x, that will be homotopic to a path in R this comma this. Now from this, how can we say? But that is looks like okay, but we have to just clearly write something which is not clear actually. So what we actually have? So we
Like maybe
actually
in the notation for homotopic class, you can add a subscript X and subscript A, and that will distinguish it. And like we'll also have to use the result from the first part that we have shown that I star is homotopic. I star is injective.
that's part we can use, right? Okay, just a minute. I'm just summarizing what we have done. So we have done. So this belongs to pi1 x comma x0. Now we have done R is homotopic to F is homotopic to R compose F, and R compose F, this one belongs to pi1 x comma x0. Okay. Oh, sorry. A comma f0. Right. Now what is my I star R compose F? Right. I got now the point. Now that is actually I compose R compose F. This one. And this one, what we have proved, that is not actually this. We have proved actually I compose R compose F. Because we have proved that homotopy class, right? You are right. So if we have used that homotopy class notations, then it will be correct actually. So here we proved that mod f, that is equal to R compose f in X. We proved this because f is a path in X. Now if we take this one, now if we take this y actually, sorry, not y. Now this is X. Now I star, now this is A. Now this A equal to this, and that was actually my homotopy class of F. Or we can write this is same as this, or we can write that this is same as R compose F homotopy class of X, and that is homotopic to F. So this is actually. So what we actually proved here. So don't misunderstood. So first of all, why we cannot write there? I have to be a little bit precise there. So here we can, why we cannot write this? See, whenever we are talking about that map F and map G, okay, then this map F and this map G are homotopy classes in A. Okay, and when we are using that I star, then they are going to the homotopy classes in X. Now it may happen that in that homotopy classes, that is in the larger class, you have more points, right? There it may happen that both paths are equal, but that does not mean that homotopy classes, that is R and F and G, will be equal. For an example, you can take that circle. Okay, and suppose this is inclusive in R2. Okay, just embed this in R2. Now note that whenever you have this circle in this, now if you have this path, now say this is your path F. Okay, say this is your path F, and say that reverse path is G. Okay, now see here that F and G, they are not equal. They are not equal in A. If you put here A, right? But if you look at that their inclusion one, this one, now G moves from this direction and F moves from this direction, but both are null homotopic in R2. So therefore, but that F equal to same as this in X, right? So it is better to, is it clear? This is this. They are same. So therefore, you cannot write here directly your I star F equal to, that is your I compose F, that is fine, but it is in a different class. So you can, if you write it is F, so this class is different. So this is your X A, and this is your X. Now you are correct that if we change it, use the different notation, then it will be fine. So I will change the notation here. So here I will write A, and here I will write that other one, that is X. Then that will be fine. Here we do not need that one, but here we need this. Otherwise we have a confusion, since we are proving that surjective. Okay, so I will change here and I will send you. Now is it clear that here why this is not equal, but that is why I star F is not F? Is this clear?
So by example, it is clear that they
No,
are
no,
not equal in S1,
it
but
is also clear. See, I star F. Okay, you can write it is F. It is actually F. It is not, I am not saying that it is wrong. It is actually F. But here it is that homotopy class is A and this is X.
okay. So if basically we use this, then we will get the homotopy class of F in X will be equal to homotopy class of G in X, but we need the classes to be equal in A. So they are
Right,
not the same
exactly.
thing.
Exactly.
Okay,
Okay.
okay, okay, okay.
So that is a good suggestion actually. So when I did this one, since actually I generally follow Hatcher, but Hatcher just said that, and he did not write each and every thing. But because of that, when I start writing, I was also a little bit confused about that one. But I use symbol, the same, I keep the same symbol, but that was misunderstood. But now that suggestion, who suggests that one, that we can write this notation here and this notations there, because this one, that did not come to my mind, that we can choose here A and here X, then that confusion will be solved. There will be no other confusion. That is a good suggestion. So I will change that in the lecture note and I will send you. Okay. So that's mean this is, we cannot do directly this, because if you write I star F, that is actually F in X, right? So therefore we cannot write, but we need this. Now everything is fine. Now here, since here, now note that what we are writing here. Now here this R, everything in X, and we are getting deformation retracts to X, right? So therefore we are actually getting here this one. We are actually getting this. So R is same as R compose this one. Now you can see, now that is done actually. Now whenever you take I star that R compose F in A, now that is same as R compose F in X, and we have proved that that is X. Okay, so we assume this is in homotopy classes in phi1 x comma x0, and we proved that its inverse image exists. So therefore, I star is surjective. Now is it clear?
Yes, sir.
Good. Now that is a good suggestion actually. That is very good suggestion. So if we write in this way, then everything is done. Then there will be no other confusion. We can use that this type of concept. So there will be lots of things. So when we have confusion, we will follow this notation only. So that different homotopy class. Then there will be no other confusion. Okay. Since we do not have sufficient time left, now I'm just quickly go through one thing. I will not solve. I will exactly solve this in the next class. Now just tell me what will be the fundamental group of S2? Any idea? Do you know what is S2? S2 means sphere. Anyone? So anyone can give me the answer. It is not only for the MSc student or BTech one. Anyone? Any idea? What will be the fundamental group of S2? You should have some guess. You have exams because this type of problems will come in exam.
Sir, same as S1?
It is
No,
0.
no, it is 0. Why it is 0?
We can retract this every point in S2 to a single point. Deformation retractor.
Right, but how?
Uh,
Any idea how? So if we take any
Can
path here,
like we can show that it is homotopic to r cube minus 0.
no, it is not RQ, not homo. No, that is homotopic. It is different thing. You did
So
not solve
that
that.
r cube minus 0 will retract to s square, r cube minus origin, and
R cube minus. No, that is a different thing. Again, you have to prove then why R cube minus. So we did not prove that homotopy yet, right? The two spaces are homotopy. We have not proved that. So we will come to this in the next lecture. But why? So if you
if
have,
we consider any loop
huh?
at any point, then we can say, then if we looks like the loop is as a boundary of some disk,
Okay.
then we can retract that boundary to a single point.
Okay. Anyway, so first of all, can you give me? Suppose you have a path. Say F is a loop from I to S2. Okay. Now, can it be surjective? I means 0, 1. So you have a path 0, 1 to S2 is a path. Okay. Now, can this path is surjective?
No.
No. Any guess why?
If we delete one point from
1 point from where?
I.
I.
It will be disconnected, but sphere will be connected.
So what? But we did not get any contradiction, right?
if f is a continuous function, then it should map connected sets to connected sets.
But it does not mean that it's a continuous map goes to disconnected to disconnected. That is not true.
So here, suppose if you consider any path in S square, that is a continuous map from 0, 1 to S square. And suppose we assume that it is surjective. So consider any arbitrary
No, no.
element of S square.
Anyway, now we are diverting, Shamar. It can be surjective. It can be surjective continuous function. Okay. So if we have this kind of map, this can be surjective. Now that is the problem. So what actually our guess, our aim to prove that. Now if we have a map this to this, now we will prove. Now suppose you have a
So, can we use like stereographic projection type of things?
right, we will use that one as well. We will use that one. Now actually what is the idea behind that, which is in the lecture note, but I could not have time to solve. But I am giving the rough idea what is there actually. Now suppose f is a map such that f of 01, this image is properly contained in some s2 minus a point, say p. If this is true, then we are done. Why? Then suppose this is my point P. Now this is it to show that homeomorphic to R2? Okay, and now you can use that stereographic projection to show that this is homeomorphic to R2. So that's mean you have a path which is in R2. Now since R2 is it can be null homotopic and this is a homeomorphic, so you can pull back to the map here. So therefore F will be homotopic to some constant one, some constant part, say E some x0. Okay, now this is true. But the problem is that here that map F can be surjective. So that is the problem. Now what we will do now for this one, now suppose we have a map, now we choose one point here, we will choose a disk here, and if you take that point, inverse image of that point will be compact, that will be this, in some way we will prove that. So now we will prove that if G is any path pi1 is 2, okay, now then we find a map F belongs to pi1 S2 such that F is homotopic to that identity and or directly we are not this wave such that G is homotopic to identity and F of this 0 1 is subset of S2 minus this point P and which is homeomorphic to R2.
Sir, G is homotopic to identity. Okay.
No, what we'll prove now, if we have any path in pi2 in S2, then we will find another map F such that G is homotopic to F and that image of F will be properly contained in this set, and that will imply F is homotopic to identity. Now G is homotopic to F is homotopic to identity, so therefore G will be homotopic to identity. So we are done. So that was the approach. Okay, so which will prove?
So what it concludes to?
That will conclude that fundamental group of S2 will be 0. Okay, fine. So anyway, so that will be in the lecture note I will send you, and then you can just quickly go through the proof. The next day I will explain that. Okay.
So, the syllabus will be up to the previous lemma or
No, syllabus will be up to only deformation retract. So there will be one application of deformation retract, but obviously that one will not be in the syllabus. Okay.